First, we will look into the unfiltered or original plot. In the coding, we can see that the parameters such as frequency included, also the length and size of the plot. The second paragraph, which is this one, of the code is used to do the plot as further, phase 1. And the following code is to determine the length and the other parameters such as frequency shifting, FFT, and so on. For the magnitude response, absolute function used, and for the phase response, angle function is used. The next code is used to plot both magnitude and phase response. This is the code used to do the magnitude and phase response, and over here we have some equation to calculate the value of magnitude of the phase of the magnitude response. And over here we have determined the length, and over here we did to the original plot. As we run the code, we will get some two figures. So the first figure is to show the ECG1 signal, which we do in phase 1. So the second signal is used to find the magnitude response and the phase response. Over here we can see that some disturbance, which the noise is also a disturbance at disturb the signal from -60 to -40 and from 40 to 60. So the fluctuation of signals are large, and from the phase response we can clearly see the noise is affecting the signal flow.
From a previous graph, we can see that the signal required is below 40 Hz, thus the passband frequency will be 40 Hz, such that the signal above 40 Hz will be considered as noise. Thus, a FIR filter is required to be designed to remove the noise. A low-pass filter with windowing technique of Hamming is used. For filter design, filter order is important. Thus, in order to find the order for a filter, we come up with a code that generates for 10 loops which add 20 order per loop, which is n equal n plus 20, and FIR1 is to give finite impulse response, and filter is to apply filter to noise influence input signal. And this is our whole coding, and by running it, we can see that at the order of 20 and 40, there's noise signal, and the order of 60 and 80, there's also noise signal here and here. And for the order of 100 and 120, we can see that there is still noise, but the noise is getting smaller. And at the order of 140 and 160, we can see a slight difference at here, which is at the order of 140, we can see a small noise at here, and there's no noise at 160. And at 180 and 200, we can see that there's no noise that's disturbing the signal. Thus, we can conclude that the order above 160 can be used to design the filter as above 160 there is no noise disturbing the signal.
This is the MATLAB coding showing the original ECG signal code and the filtered ECG1 signal. So we have setting the bandpass filter at 40 Hz. The omega C, the order of the filter is n equal to 160. Is a FIR low pass filter with Hamming windowing technique. So here is the original ECG1 signal plot, and here is the frequency spectrum of the plot, and here we have the filtered ECG1 signal and the coding for its frequency spectrum. Now these four graphs shown the result of the MATLAB simulation after compounding. So we can see that this original graph have noise compared to this, as is filtered by the filter. And here is a frequency spectrum original ECG1, and this is the frequency spectrum of filtered ECG1 signal. So we can see that the spectrum after 40 Hz is being filtered out.